Hello and welcome. My name is Jason White, a PhD student with the Optimal Robotics Lab at the FAMU FSU College of Engineering. Today, I'll be presenting my work on avoiding dynamic obstacles with real-time motion planning using quadratic programming for varied locomotion modes. Generating trajectories with obstacle avoidance is necessary for robots operating in the real world. Whether it be stationary obstacles, such as a hole in the ground, or dynamic obstacles, such as dodgeballs, we aim to generate motion plans on the fly that both avoid stationary and moving obstacles. Generating avoidance-based motion plans has been a key focus of study, with researchers developing methods such as optimal reciprocal collision avoidance, which guarantees collision-free motions by disallowing velocities that would result in a collision, and its extension, decentralized collision avoidance, which uses linear model predictive control with flatness-based quadratic dynamics. Furthermore, nonlinear MPCs are solved at 20 Hz using the Panox solver and can avoid multiple moving obstacles as seen here. Finally, second-order cone programming generates motion plans around obstacles using soft constraints at rates comparable to the previous method. These methods produce impressive results. However, we want a method that works with multiple dynamic obstacles across locomotion modes, formulated as a convex problem so we can reliably generate solutions, and develop solutions faster than the previous methods presented. The method proposed here enables trajectory generation with avoidance in real time, i.e. milliseconds, using quadratic programming. It also scales to additional dimensions for multiple obstacles and adversaries, which we numerically validate with a parameter study, and can be used with a large number of dynamic obstacles. We also demonstrate the approach with varying locomotion modes, including bipedal walking, and show effective avoidance in dynamic hardware experiments with physical actuation limits. We want to generate a trajectory while planning around obstacles, and do so using a convex solver. Considering the nonlinearity associated with the Euclidean distance formula, we decide to use a half-space representation of the obstacle to relax our optimization into a convex one. This simplification allows for the inclusion of avoidance constraints while maintaining fast solve times, assuming the optimization is feasible. However, implementing this method on hardware showed us that the optimization was frequently infeasible, causing the planner to fail. We instead expand the formulation by adding two additional components. One uses the previously generated trajectory to approximate these half-space constraints at each node. The second adds a soft constraint at some defined distance from the obstacle, which allows the user to get close, but in turn penalizes the cost function. To achieve this, we introduce a slack variable encoding constraint breaches and square the soft penalty in the cost function, leading to the QP formulation seen here. In the following slides, we demonstrate that reduced order linear plant models are effective with high degree of freedom terrestrial and aerial vehicles. When simulating the double integrator, we find the agent strategically avoids an accelerating obstacle. Extending this method to multiple obstacles yields similar results. Instances seen here have 5 adversary obstacles simulated in 2 and 3 dimensions. The soft constraint radius around each obstacle is represented as the black circle or sphere, and the optimal trajectory generated is the black dashed line. Using a simple PD chase law with randomized gains, the adversaries pursue the agent. Further extending this, we find agents avoid each other without any agent-to-agent coordination. We accomplish this by treating the agents as moving obstacles with unknown paths and independently generate trajectories for each one. To understand the effect of our soft constraint, we simulate the 2D system starting with no soft penalty and ending with a penalty 1.5 times the obstacle radius for 1 through 10 obstacles. The agent is tasked to travel to a goal with adversarial obstacles placed directly in its path. We find that the increasing soft radius improves the success rate, especially when avoiding a large number of adversaries. We then test this method with another system, more specifically a linear inverted pendulum model. Using MPC with the LIP model, we predict 3 steps into the future. By including avoidance, we simply command the robot to walk forward and find it avoids an obstacle placed directly in its path. When applied to a 20 degree of freedom Cassie series robot, we again see it navigates around the obstacle. A low-level operational space controller commands joint accelerations, which allow the pelvis to follow a trajectory developed by the presented model. I want to recognize Tianzi Wang for his hard work on both the LIPM avoidance integration and the operational space controller seen here. Using the same simple double-integrator model previously discussed, we generate trajectories for a quadrotor in 2 dimensions. Much like the simulations, the second drone uses a simple adversarial PD chase law. MPC is used as a mid-level motion planner, with low-level control coming from a Mellinger-style controller included in the Crazy Swarm software package, developed at the University of Southern California. Extending this to 3 dimensions, we find that the avoiding agent in blue is able to escape the adversarial agent in red. You'll notice that the adversary frequently crashes. This is a consequence of downwash from the avoiding agent that is not accounted for in the simple chase law. Finally, we try some more complex scenarios, such as multiple swinging obstacles in the drone's path. Here we've presented a soft piecewise constraint that penalizes the cost function when an agent passes an obstacle at risk distance as computed by the half-space relaxation, a numerical and physical parameter study that quantifies the reliability of the soft constraint formulation, and finally, a validation of the method on multiple simulated and hardware systems with varying dynamics. I want to thank the Mechanical Engineering Department at the FAMU FSU College of Engineering and the Toyota Research Institute for supporting this work. I also wanted to thank my co-authors, PhD researcher Tianzi Wang, Master's Research Assistant David J., and my faculty advisor Christian Hubicki for their contributions to this work. Below is a link to the originally submitted video to IROS which accompanies this paper. Thank you for your time, and I look forward to answering your questions.